All right, today we are doing linear, quadratic, and exponential models. We've worked with all these different kinds of situations before, and now we're just looking at how we can recognize which categories an equation or a graph or a table will fall in. And so, as a reminder, we already know a linear function is a function where you have a degree of 1. And remember, if we don't have an exponent, we know it's 1. And the degree is the largest exponent in the equation, so a linear function has 1. And if you see it on a graph, you know that it's a straight line. That's where linear comes from. Exponential functions usually have the exponent is your variable. That's the unusual part of an exponential function, is your variable is actually in the exponent. And there's two kinds. We've seen growth, which from left to right go up. And remember, they approach an axis of symmetry, or not an axis, an asymptote, which is a line that they approach and they go on and forever and never touch. This would be what a growth function looks like. A decay function would go in the other direction. But those are both exponential. A quadratic function, which is what we've most recently been working with, is when we have a degree of 2. And if we saw that on a graph, those are parabolas, which are U-shaped curves. Sometimes they are up. If we have a negative a term, it faces down. But quadratic functions have a degree of 2, and they have parabolas, which are U-shaped curves. So that's how you can tell what they are, by looking at the equation and looking at the graph. So if we look at some equations, and I ask you to choose a model from an equation, first thing we're going to do is look at the degree. So in A, our degree is 1. A degree of 1, we know that this is a linear model. The next one, I look at the degree is 2. And when it's a degree of 2, I know it's a quadratic function. And I'm going to just remind you of the different forms of the quadratic just so that we don't forget. This is in standard form. And remember, standard form is when the variables have their exponents lined up from biggest to smallest. So this is the 2, the 1, and the constant. So if it's in standard form, this is what it looks like, and that's a quadratic because the degree is 2. And see, if I look at the exponent is actually the variable. When the exponent is the variable, that's exponential. Next one, I'm going to go back, look at the exponent. My exponent, my degree is 1. That's the largest exponent I have. So this is linear. On the next one, I have a degree of 2. We know that 2 means it's quadratic. My next question is going to be, what form is it? And this is still in standard form because the terms of the polynomial are listed in from highest to lowest degree. So this is also in standard form. The reason it looks different and only has 2 terms instead of 3 is we simply don't have a b term. We don't have the x term in the middle. And that's okay. It's still quadratic because it still goes from biggest to smallest degree. Okay, then next we have a different form of quadratic. And this is the one where we have 2 parentheses, and those 2 parentheses will indicate what our x-intercepts are. And so we call this the intercept form. Next one, again, our exponent is our variable. That means that it's exponential. And this last one is quadratic. This is one of my favorite forms of a quadratic. When you have a single parenthesis squared, that form is vertex form. And the reason I like it is it's really easy to figure out what your vertex is without really having to do any work. So that's the vertex form. That's H. So we've shown that no matter what the equation is, we can tell what kind of model it is. We can also choose a model by looking at a graph. And so for this first one, I'm going to graph all of these points. And when I graph the points, I'll be able to see what kind of shape it is, and that will determine what kind of model we have. So I'm going to start with negative 3, 6, negative 3 and up 6, negative 2 and up 2, 0 and down 2, over 3 and up 6, to the right 1 and down 1, and to the right 2 and up 2. And if you look at these are forming a parabola, and we know that a parabola makes it a quadratic model. So we know it's quadratic if it has a degree of 2 or it has a parabola. Next one we're going to do, again, we look at those points. We don't know until we actually graph the points and we can see how they look. I've got negative 2 and up 5, 0 and up 3, over 1 and up 2.5, and over 2 and up 2. And this is coming down and then starting to slowly change direction. And so that shape is exponential. Now all I'm asking is what model it is, but as long as we're looking at that, let's look at what kind it is, because it's coming down from left to right towards the asymptote. This would be a decay function. It's a decay exponential function, but the part that we really cared about right now is that it's exponential. Just adding a little bonus information in there for you. Okay, we're going to try these points and see what they look like. If I have a negative 2 and up 4, positive 1 and down 2, oh, I missed this one, negative 1 and up 2, and over 2 and down 4. So I've got negative 2, 4, negative 1, 2, over 1, 2, and over 2 and down 4. And these are forming a straight line, and that makes these linear. So that's all things based on things that we've learned previously regarding exponential, linear, and quadratic models. What I'm going to do next is I'm going to sort of take it to the next level, and we're going to be able to look at a table of values to determine whether it's linear, quadratic, or exponential. And so the first test is to determine if a function represents a linear model from a table. We're going to test for what's called a common difference. And when we look for the common difference, what that means is we take a second value and subtract, because difference means subtract. We're going to subtract the previous value. That's what a difference is. And that's how we're going to find these. So here, if I take the second value, the 2, minus the previous value, negative 2. 2 minus a negative 2 is positive 4. And be really careful when you're subtracting a negative. We know that when we subtract a negative, that means we're actually adding. If I take 6 minus 2, I get 4. And if I take 10 minus 6, I get 4. Now I do always look to make sure that these differences are all the same so that we're comparing apples to apples. And for the purposes of our notes, all of our x's are going to be a distance of 1 apart so that we can really focus in and zoom in on the y's. Since all of these are the same, this is a common difference. Common because they're the same. Difference is what you got when you subtracted. And anything with a common difference is linear. So that's how you can use a table to determine if they have a common difference. Now, to determine if a function is a quadratic model, by looking at the table, we're going to look for a common second difference. So the second difference is the same concept. The difference means we're taking a value and subtracting the previous value. So we don't go down, we take this and we take the one above it and subtract it. So if I take 2 minus 16, that's a negative 14. Negative 2 minus 2, that's a negative 4. Okay, so we already know they're not a common difference because I've got negative 14 and 4. 4 minus a negative 2 is 4 plus 2, which is 6. 20 minus 4 is 16. And 46 minus 20 is 26. Now clearly those are not a common difference. So I'm going to see if I have a common second difference. And all that means is I'm going to do the same thing one more time with these values. Negative 4 minus a negative 14 is negative 4 plus 14, which is 10. 6 minus a negative 4 is 6 plus 4, which is 10. 16 minus 6 is 10. And 26 minus 6 is 10. When you do it the second time, that's called a common, because now they're all the same, but they're all the same on the second difference. And when that happens, it's a quadratic. Okay, so you do the difference, and then you do the difference again, and that makes it a quadratic. The last one we're going to do from a model of tables is going to be to find the exponential model. And for the exponential model, we look for a common ratio. So this is different. We're going to do something different than we did with quadratics and linears. And out here, I'm just going to let you know that a ratio is where we take the second point, kind of like we took the second point to subtract. We're going to take the second point and we're going to divide. It's going to be divided by the previous point, or the previous value. So again, we start with this, and then we're going to divide by that. So I start with the second point, which is 1/3. I'm going to divide by 1/9. And I know it's been a bit, and I know you guys love fractions, but when we have fractions, that means we multiply by the reciprocal. We don't actually ever divide in fractions. If you are dividing two fractions, you take the first fraction and you multiply by the reciprocal. You flip it over, of the second fraction. Then, of course, when we multiply fractions, we multiply across the top, and we multiply across the bottom, and then we simplify. 9 divided by 3 is 3. So my ratio of this first one is 3. I'm going to do the same thing here. I'm going to take my second number divided by the previous value, which is 1/3. Now I need a common, I'm going to put the 1/1 so that I have a fraction. Take that whole number and make it a fraction. But I'm going to multiply by the reciprocal. 1 time, and multiply across the top. 1 times 3 is 3. 1 times 1 is 1. And 3/1 is 3. So far I have a common ratio. Let's see if that continues. Okay, these are going to get easier because we don't have fractions anymore. 3 divided by 1 is 3. That was easy. And second one, 9 divided by the previous, 3. 9 divided by 3 is 3. Since these have a common ratio, they're all the same. Common means they're the same. That means it's an exponential model. And what I want you to notice about the exponential model, we went from really small fractions up to 9 pretty quickly. That's pretty common when we have an exponential model, is that the values change very drastically, very quickly. And so that's a way that we can kind of eyeball which method to start with. And so let's take that into consideration while we look at these tables. On the first one, if I'm going from 4 to 5.8, and even though these are small numbers, see how the decimals expand pretty quickly? That's an indication that we might have exponential. That's probably where I would start. Instead of starting with a common difference, I'm going to start with the ratio because of how this looks. It looks like it grows decimals pretty quickly. So I'm going to take the second number, the 4.4, divided by the previous value. And 4.4 divided by 4 is 1.1. I'm going to take 4.84 divided by 4.4. That also happens to be 1.1. And make sure you use your calculators and divide it out. 5.324 divided by 4.84 is 1.1. And then this last one, let's just make sure it works. 5.8564 divided by 5.324 is 1.1. All of these ratios are the same. That means I have a common ratio, and that's exponential. Okay, next I'm looking at the next one. These look like they go at a pretty reasonable rate, like close to the same rate, if not the same. So I'm going to start with the difference here. 1 minus 1/2 is 1/2. 1 1/2 minus 1 is 1/2. And 2 minus 1/2 is 1/2. I just have to do it once. I have a common difference. I I only had to go through it once, which means that it is linear. Okay, finally I'm going to look at this. It goes from 0 to -8, but it doesn't look like it goes at a crazy rate, and I don't have decimals exploding on me. So I'm just going to try the common difference thing real quick. I have -0.5 minus 0 is -0.5. -2 minus a -0.5 is -2 plus 0.5, which is -1.5. Okay, so I don't have a common difference. Let's go see what we've got, and if we need to go another round, we can. -4.5 minus a -2 is -4.5 plus 2, which is -2.5. And -8 minus a -4.5 is -8 plus 4.5, which is -3.5. But these, 1.5 minus a -0.5, -1.5 minus a -0.5 is -1.5 plus 0.5. That got kind of convoluted, didn't it? It's -1. -2.5 minus a negative is -2.5 plus 1.25, or 1.5, which is -1. And -3.5 minus a -2.5 is also a -1. This, I had to go 2 rounds, so this is a common second difference. So this is a quadratic. So that's how you can determine if something is exponential, linear, or quadratic by looking at the equation, the graph, and the table.